Good morning, dear students. We have started a new chapter, that is S block elements. And in S block elements, we have covered two very important definitions, that is of ionization potential and electron gain enthalpy. Now, the next part, that is the classification of periodic table into different blocks. Some elements belongs to S block, some elements belongs to P block, some elements belong to D block, and some elements belong to F block. Now, on what basis this classification has been made? So for this, let us talk about the energy levels or shell. You know it very well that outside the nucleus we are having energy levels, or which are called shell, where electron revolves around the nucleus. Distance of the energy level is having a fixed value in every atom, and the distance is different for each and every atom. It depends on the force of attraction between electron and the nucleus. So these energy levels or shell, that is K, L, M, N, etc., 1, 2, 3, 4, are further classified into subshells. Shells are further classified into subshells. So here, energy levels or shells are further classified into subshells based on their shape. The subshells are of four types, and the four types are: number one is called S subshell, number second is called P subshell, then we have D subshell, and at last we have F subshell. S subshell, P subshell, D subshell, and F subshell. S subshell is having a spherical shape, just like ball. These are the axes. P subshell is having dumbbell shape. D subshell is having double dumbbell shape, and for F subshell the shape is complex. F subshell is too diffuse, it's too complex that its shape cannot be drawn. So S is spherical, P is having dumbbell shape, D is having double dumbbell shape, and F is having complex shape. S subshell can accommodate maximum of 2 electrons. P subshell can accommodate maximum of 6 electrons. D can accommodate 10 electrons, and F subshell can accommodate maximum of 14 electrons. S can accommodate 2 electrons, P can accommodate 6 electrons, D can accommodate 10 electrons, and F can accommodate 14 electrons. Now, next one. As the first energy level is very close to nucleus, it is having smallest size. So first energy level can accommodate only one subshell, which is designated as 1s. S subshell, which belongs to first energy level, is called 1s. S subshell, which belongs to second energy level, is called 2s. S subshell belongs to third energy level is called 3s, 4s, 5s, 6s, 7s, and so on. So for first energy level, we can have only one subshell possible, which is called 1s. Now, Move to the next one, second energy level. For second energy level, size increases as we are moving away from the nucleus. So second energy level can accommodate two subshell, that is 2s and 2p. 1p is not possible. P is possible with second energy level. So in second we can have 2s and 2p. Next one, that is third energy level. Size further increases of the energy level. It can accommodate three subshell, that is 3s, 3p and 3d. So D is possible with 3d. Move to next, fourth energy level. For fourth we can have four different types of subshell: 4s, 4p, 4d and 4f. So for first we can have only one subshell, that is 1s. For second we can have two, that is 2s and 2p. For third we can have three different types of subshell, that is 3s, 3p and 3d. And for fourth energy level we can have four different types of subshell, that is 4s, 4p, 4d and 4f. S subshell can accommodate maximum of 2 electrons. P can accommodate 6 electrons. D can accommodate 10 electrons and F can accommodate 14 electrons. Now why first energy level is having capacity to accommodate 2 electrons? According to Bohr-Breuil scheme, 2n square. This is the formula for the calculation of number of maximum electrons that can be accommodated in any energy level. If we put n equals to 1, we want to calculate the number of electrons which can be accommodated in first energy level. 1 into 2, that is 1. 1 into 2 is 2. In first energy level we can accommodate maximum of 2 electrons. Reason is very simple, because in first energy level we can have only one subshell, that is called 1s. And S subshell can accommodate maximum of 2 electrons. That's why for first energy level only 2 electrons can be accommodated. Now, about the classification of periodic table. If the last electron, which is also called incoming electron, moves to S subshell, then the element belongs to S block. If the last electron or the incoming electron moves to P subshell, then it is called P block, it belongs to P block. If the incoming electron belongs to or moves to D subshell, then the element belongs to D block. And if the incoming electron or the last electron enters F subshell, then the element belongs to F block. So the classification of periodic table into different blocks is made on the basis of entry of last electron. To which subshell the last electron is making its entry. Then about the S block. As S subshell can accommodate maximum of 2 electrons. So for S block we are having two groups. That is group number 1, which is also called first A, and group number 2, which is also called second A. Hydrogen is not written here because its position is a matter of debate. Hydrogen resembles non-metal as well as metals. Some properties of hydrogen resembles metal. Some properties resembles to non-metals. That's why this hydrogen is placed separately and it is studied differently. It is not included with the group 1. It is studied separately. So here group 1, first A, and then we have group 2, that is second A. Group 1 of first A is also called alkali metals, and group 2 or second A is also called alkaline earth metals. Alkali metals: lithium, sodium, potassium, rubidium, cesium and francium. For all these members, the general electronic configuration is N-S1. N represents the valence shell. For second A, the general electronic configuration is written as N-S2. You know it very well, S can accommodate 2 electrons. So for, if 1 electron is there in S, then the member belongs to group 1 or first A, which is also called alkali metals. And if S contains 2 electrons, then the element belongs to group 2 or second A, which is also called alkaline earth metals. First member of group 1 is lithium. As lithium belongs to second energy level. So for lithium, valence shell will be second. So its outermost electronic configuration can be written as 2s1. Move next. Sodium 3s1, 4s1, 5s1, 6s1 and 7s1. Lithium, sodium, potassium, rubidium, cesium and francium. 2s1, sodium 3s1, potassium 4s1, rubidium 5s1, cesium 6s1, francium 7s1. Francium is radioactive in nature. Then group 2 or second A, beryllium, magnesium, calcium, strontium, barium and radium. Again radium is radioactive in nature. It emits harmful radiations like alpha, beta and gamma. Be belongs to second period. So valence shell will be second, as 2 electrons can be accommodated here. So its electronic configuration outermost will be 2s2, outermost for magnesium 3s2, 4s2, 5s2, 6s2 and 7s2. So it is about the general outermost electronic configuration for group 1 and group 2. Group 1 first A, group 2 second A. In the valence shell of group 1 or first A, we are having 1 electron, 1 valence electron. And in group 2 or second A, we will be having 2 valence electron. 1 valence electron present in S subshell, 2 valence electron present in S subshell. Now let us talk about group 1 of first A, alkali metals. General electronic configuration is Ns1. These metals are called alkali metals because the oxide reacts with water and produces a strong base which are called alkali. Except lithium. NaOH, strong base, alkali. KOH, strong base, alkali. So why these are called alkali metals? Reason is simple. The oxide reacts with water and produces a strong base which are called alkali. In any period, alkali metal forms the first member of the period. So let us talk about some general physical properties. First one is atomic and ionic radii. It is the first member of any period. One electron in outermost shell. According to atomic number, protons are there inside the nucleus. If we have more electrons in the valence shell, then force of attraction between the nucleus and the valence electron is more, which results in contraction of valence shell. Here we are having only 1 electron. So the force between the nucleus and the electron is less because we are having only 1 electron. If we increase the electron, force of attraction will increase. So as it is the first member, its atomic size is maximum or its ionic size is maximum. But we'll talk about atomic size, not about ionic size. Let us talk about atomic size only. As it is the first member of any period, that's why its atomic size is maximum. When we start moving from left to right in a period, atomic size will decrease due to increase in number of electrons in the valence shell. Valence shell remains same in the same period. So when we increase the electron, number of protons also increases in the nucleus, due to which force of attraction increases between nucleus and electrons of valence shell, as a result of which valence shell undergoes contraction. So whenever we talk about atomic size, alkali metals will be having the maximum atomic size, as it is the first member of any period. Now, if we move down in a group, what happens? If we move from period second to period number third, there is progressive addition of energy level. Shells are added. Valence shell changed. Here it is second energy level as valence shell, and here it is third energy level as the valence shell. When there is an increase in the energy level, the distance from the nucleus increases. So what happens? Size will increase. It's a rule. So if we move down in a group, then atomic size increases due to progressive addition of energy level. Then the next one is ionization potential. Ionization potential proportional to 1 by atomic size. More the atomic size, less will be the value of IP. Less easily the electrons can be removed. Less energy will be required for the removal of the electron. As alkali metals have the maximum size, so they are having least value of IP in any period. If we talk about second period, lithium will be having the least value for ionization potential, because it is having maximum size in second period. Force of attraction between electron and nucleus is less. By providing less energy, electron can be removed. If we move from top to bottom, what will happen? Atomic size increases, due to which force of attraction between valence shell electron and nucleus decreases. Value of IP will decrease. Less energy will be required to remove the electron. Then we have oxidation state. All these metals have one electron in their valence shell. By losing one valence electron, they will acquire the electronic configuration of nearest noble gas. Like lithium, if loses one electron, it becomes Li plus. And Li plus, it is the electronic configuration of helium. Configuration of helium is stable. Similarly, if we talk about Na, by losing one electron, gets converted to Na plus, and Na plus is having electronic configuration of argon. The configuration is stable. So here we can say that as there is only one electron in valence shell, all alkali metals, by losing one electron, gets converted to unique positive ion, M plus ion. So for all, the oxidation state will be plus 1. Reducing property. Tendency to reduce others. They are alkali metals. They have large atomic size. Electron losing tendency is easy. So they can donate electrons easily to other species. So we can say here that they have a strong reducing property. A strong property, strong tendency to reduce others. Then we have next one, metallic character. Metallic character. What is metallic character? Metals are those elements which have electron losing tendency. If an element can lose electrons easily, it is called more electropositive, or it is called more metallic. So in any period, alkali metals have the maximum metallic character. As you move down in a group, metallic character will increase, or we can say electropositive character will increase. Tendency to lose electron will increase. Alkali metals have maximum electropositive character, or they are most metallic in the periodic table. Then we have flame coloration. When alkali metals or their salts are heated in Bunsen burner flame, then these metals or their salts impart a characteristic color to Bunsen burner flame. Means they will provide color to the Bunsen burner flame. So all these points are very important whenever we talk about alkali metals. So this is all about general physical properties. In next lecture we will talk about chemical properties of alkali metals or chemical reactions of alkali metals. Thank you and have a good day.